occur frequently and does not last longer than say a few minutes or few hours. So for that purpose, what we need to be rational in assuming the total loads acting. So we go for combining the loads. So IS code 6512 states that we should consider three stages at least for the construction or load calculation, and these three stages are load combination A, load combination B, load combination C, and they need to be considered first while the construction is going on. So there are chances, if we do not consider, that cracks develop on the upstream or downstream side. Even if we are taking care of load combination B or C, load combination A sometimes become detrimental during the construction time. So we should not forget that construction condition, while dam is being constructed, we should follow load combination A and we should check the stability of the dam, the no cracking of the concrete in the dam as per the IS code combination. So this is the first, that construction condition, when there is no water. Construction condition means there is no water, dam is empty, so its own weight is acting onto it, and apart from that certain other forces are taken into consideration depending upon the height of construction. The second being load combination being normal operating condition of the reservoir. Yeah, this term you could think about the normal operating condition of the dam or reservoir. This is full reservoir elevation. It's not high flood, but full reservoir. Normal dry weather tailwater, if exists, some tailwater. Tailwater means on the downstream side. Normal uplift means our drainage system. Whatever drainage system we have, drainage gallery or drains constructed down into or through the dam wall, they are all operational, and ice and silt we apply as per the condition of the geography. So this is a load combination B, and we calculate loaded and calculate the stresses based on this normal operating condition. Then comes the third condition, that in case of flood, what happens? So flood discharge condition. These are three basic conditions. Otherwise, in this condition, what else are taken flood condition? Because here we are considering the HFL height, so that would lead to more the uplift, more hydrostatic pressure, more wave pressure with this combination. So reservoir at maximum flood pool elevation, all gates are open, tailwater at flood elevation, normal uplift and silt if applicable. So this is the combination. Now these three combinations are added with certain additional top-ups. So look at these A, B, C, D, E, F, G. There are total in total 7 conditions given by the IS code, but 3 basic conditions. What is the fourth? That load combination A during the construction stage, but with earthquake. We calculate this also. Sometimes load combination D, if your location geography of the dam is in zone 5 of earthquake, which we have seen that certain part like Bhuj and other areas are falling into the more severe this earthquake prone areas. So what we do combination A during construction, even we take care of the earthquake waves. The fifth or E combination as per the IS code is combination B, that is normal pool level with earthquake. Okay, with earthquake. Now F and G, last 2 conditions, are special condition when there is no drains operative. That means your seepage is not taking place properly. Means there is lot of uplift, but extreme uplift. Drains are inoperative, water is not getting released, not going downstream through the system which we have created. Then all the drains are inoperative. And what it is leading? It is leading to extreme uplift, the soil or the foundation is full of saturation, and the water in the foundation or into the dam of dam's body, that provides such large uplift. And this is load combination C. What is C? Flooding condition with extreme uplift. And the last one is that the E plus extreme uplift, that is the normal pool plus earthquake plus uplift. Normal pool plus earthquake plus uplift. This C is the flooding plus extreme uplift, but no earthquake here. No earthquake. Earthquake is one. This D, E, and G. All three are carrying the earthquake waves, but the F combination doesn't include the earthquake forces. That means that it is in zone 2 or 3. So I think these load combinations, 7 load combinations, are well understood. And as per these combinations, they depend upon the geography where you are constructing or where you are in charge of such projects. And you need to deal with that, which combination at what time of construction to be considered for analysis, and accordingly the design should be done. Now let's go to the failure modes. If we pick up any, and then how this structure could fail. So, or what is required for to maintain the stability of the concrete dam, that need to be taken care of. So there are basically, as I mentioned many times, basic 4 type of failure. Basic 4 type of failure, or the mechanism or the such operations could take place for the failure of the gravity dam. Mostly when we say gravity dam, you may consider both the concrete dams, the masonry dams, and mostly high dam. Small dam may differ a bit, but looking at this, let me clear the doubt that high dams means 90 meter and up. Mostly when we do the calculation, what is high, what is low. So as per the concrete characteristics and the calculation done, that what describe exactly the high and what describe exactly the low, then it comes out based on the design and construction technology that 88 meters somewhere. If we are using M30 concrete, then for M30 concrete it is 88 meter height, which is the sandwich line between the high dams and low dams. But for any dam, failure may take place because of such reasons, and these are like overturning of the dam. The dam body like this overturns. What is overturning? That this, because of the destabilizing forces on it, it overturns, it falls like this. खड़ा खड़ा ही गिर जाता है ना घोड़ा कभी कभी, तो उसको ओवरटर्निंग हो गया. बेस पे ज्यादा कुछ नहीं हुआ, लेकिन ओवरटर्निंग फेलियर इज रेयर बिकॉज बिफोर इट ओवरटर्न्स लाइक दिस इट फेल बिकॉज ऑफ स्लाइडिंग. क्योंकि ये इतना ऊपर का जो पोर्शन ओवरटर्न का मतलब हुआ जड़ों से निकल के यहाँ गिर गया उल्टा, और सारा का सारा जो पानी स्टोर किया हुआ था हमने, कितना 9,000 और 6,000 MCM मिलियन क्यूबिक मीटर इन द सरदार सरोवर. तो इतना पानी जाएगा तो भरूच 2-3 जिले तो वॉश आउट हो जाएंगे. तो इतना जो ओवरटर्निंग यदि पॉसिबल नहीं है, ये इससे पहले क्या होगा, इसका सर्टेन पोर्शन स्लाइडिंग में ही फेल हो जाएगा. जैसे ये सेकंड है ना, स्लाइडिंग में यहां से ये पूरा डैम यहां से है, तो कहां से फेल हो जाएगा, किसी भी एक सेक्शन पे फेल हो जाएगा. यहां से भी हो सकता है, यहां से भी हो सकता है, या फाउंडेशन लेवल पे भी हो सकता है. तो ये या तो स्लाइडिंग में फेल हो जाएगा, या कंप्रेशन का मतलब हुआ कि इसका जो टो है वो क्रश हो जाएगा. जैसे ये ऐसे घूमने लगेगा, ओवरटर्न होने लगेगा, यहां से टो क्रश होगा. टो क्रश होते ही ये क्रशिंग कंप्रेशन फेलियर में आ जाएगा सारा का सारा, क्योंकि रिजल्टेंट जो फोर्स है. जो resultant force है that will go out of the toe. Please mute your mics, all of you, so that the noise can be reduced. Okay. So let's do once again this, and I'll take the ink, this color. Okay. So sliding failure, cursing, and tension failure is what? If I take the DEM section like this, then tension failure is always onto the heel. This is toe. This is toe. This is heel. Tension crack. I mentioned many a times that tension even in uplift I have shown you tension crack. So tension crack generate here, but the failure takes place ultimately because of crushing, because resultant force moves out of the toe. So when we do calculation of resultant forces because of the stresses getting generated or set into the DEM body, then the tension is not directly the result, the cause of failure, but tension crack which generates here onto the heel side lead to crushing of the toe or the resultant going out of it, and the whole body of the DEM will get tilted or overturned like. So that is what is this type of failure. So what it states, the IS code said that DEM shall be safe against overturning at any plane. What is plane? Horizontal plane. This plane is say a 10 meter below the top height. This is 20 meter and so on. So any plane, even at the foundation and in the foundation. In the foundation means what? Say we started concreting on the igneous or say impervious rock foundation. So even rock we are looking at that there should not be any kind of possibility of the sliding. Overturning definitely won't take place in the foundation. It would take place only at the base. So DEM shall be safe against overturning at any place within the DEM, at the base, or at any plane below the base. It mentions at any, but it is rare. The DEM shall be safe against sliding on any plane or combination of planes. Two plane we can take combination within the DEM, the foundation, or within the foundation. The safe unit stresses in the concrete or masonry of the DEM or in the foundation. Why it writes the safe stresses? You look at this term used in the IS code, that safe unit stresses in the concrete or masonry of the DEM or in the foundation material shall not be exceeded. Whatever the safe stresses we take, they should not be exceeded. Otherwise, the last two types of failure, the chances would go up. So we need to take care of that. There are certain other provisions in the IS code. So we are going to look at first three slides, the provision of the shape of the DEM and curvature in its layout are pertinent in regard to the stability and more favorable stress conditions. Whenever possible, DEM and foundation design should take advantage of the favorable conditions accruing from curved shapes, gradual transition, and fillets. I think you could understand the kind of geography we take that I mentioned while showing you the contour map, that how we take it. If it is a small deep gorge, we could go for a arc DEM like this, and otherwise if it is like the foundation is, we go for straight gravity kind of structure, gravity DEM. So those kind of mentions here based on the DEM is composed of individual transverse vertical elements. This is important here. DEM is composed of individual transverse vertical elements, each of which carries its load. Unit length. We consider unit length while calculating the forces. So this is what is the assumption, carries its load to the foundation without transfer of the load from or to adjacent element. So those lamina or transfer these elements does not transfer load to the side lamina or elements, but directly take load to the foundation below it. So that is what is mentioned. But however, this is also mentioned that we need to check sometimes that, however, in the stability analysis of gravity dam, it becomes frequently necessary to make analysis of the whole block. Means if it is a kilometer long, 1,000 meters, then we should analyze it at a go. But initial stages we do not do. Initial stages we do design a cross section at a particular location and we go ahead with those designs. This is checked only at a particular location, like galleries are provided, then sluices are provided, and many times and now computational facilities are available, so whole block can be checked through the software. So that check should be run properly. So that is also a mention in the code. That the vertical stress varies linearly from upstream phase to downstream phase on any horizontal section. Horizontal section. This is about the vertical section. This is all about vertical, and this is about the horizontal plane. So vertical stresses varies linearly from upstream phase to downstream. If variation we look at, then it's a linear variation. That is assumption. This is about the reaction of foundation. Foundation means the impervious rocks, or you could say igneous or basalt kind of rocks, which are give good foundation. So those, the resultant of all horizontal and vertical forces should be balanced by an equal and opposite reaction at the foundation, which you study long back. For the dam to be in static equilibrium, location of this force is such that the summation of moments is equal to 0. The distribution of the vertical reaction is assumed as trapezoidal. The problem of determining the actual distribution is complicated by the horizontal reaction, internal stress relations, and other theoretical considerations. Okay, now let's have a kind of analysis that we are going to understand that all 4 type of failure. How could we protect our structure against this kind of failure? How to do the design? So first is overturning failure, and overturning failure is can be checked, can be managed if we manage the righting moments and the overturning moments. The difference of overturning and righting moments which provide stability, the forces causing moments which provide stability to the structure. Overturning moments, the forces which leads to failure or which are cause of the failure, like the hydrostatic force, like waves. All those are the overturning moments. What is the righting moments? The self weight of the dam, and many times this weight of water which is directly having vertical down component. So those are the righting moments, and we take moment about the toe. So that is the thing here. The factor of safety against overturning is defined as the ratio of righting moment to the overturning moment about the toe, and it should be more than 1.5. The thing which I was discussing is mentioned here, that before gravity dam overturns bodily, other type of failure occur. A gravity dam is therefore considered safe against overturning if the criteria for not, if other criteria are already analyzed and they have been met, then we need not to really look into the righting and overturning moments, and we could safely assume that the dam is safe in overturning if they are safe in these criteria. Okay, so I think this is understood. So let's go to the second type of failure, or the sliding. So how the basic reason of sliding is the horizontal forces, and they are resisted by friction and shearing forces. Shearing means cohesion of the material. Shearing means, and this is mu along horizontal plane. So at any plane of the dam, if it is high dam, then we calculate this kind of do the analysis at 5-meter interval or 10-meter interval from the top up to the bottom into the foundation. So these two, the friction and shear, should be enough to check the horizontal components so that there is no sliding failure. If horizontal forces causing sliding are more than the resistance available, resistance is available because of these two. Sometimes it is only friction. If there is no cohesion in the material, then what is only friction? Due to friction and shear, if it exists, shear strength, shear stresses, then both are combined. Otherwise, friction is taken care, will take care of the horizontal forces. This point, what it states based foundation, shear strength develop at the base if benched foundations are provided. The foundation is not straight but benched zigzag way, and this give us the shear strength, provides shear strength, and other joints if joints are carefully laid so that a good bond develops between foundation and concrete at the base. So this is important. The sliding resistance is a function of cohesion inherent in the materials, concrete, at their contact and the angle of internal friction of the material at the surface of sliding. So these two are the important. The junction plane between dam and rock is rarely smooth. This is rarely smooth. In fact, special efforts are made to avoid this condition, that they should not be smooth. Foundation to the concrete, the plane, the base, which we see onto the books, textbook, reference books, that a straight line, but it is not a straight line. It is zigzag undulated as per the geography or topography of the rock on the top surface of the rock, and we do not pay attention to make it smooth to create more resistance at the base. Now, to compute the factor of safety against sliding, this formula, and this should not be less than 1. So sometimes you may be amazed with the value of 1 here. Here that factor of safety in sliding, why it is kept 1. Look at this. The following equation and shall not be less than 1. This is as per the code, and the reason behind that is the factor of safety F5 and FC are used internally twice, one for friction and one for cohesion. So this is what mu is equal to 10 phi coefficient of internal friction of the material. So that varies from 0.65 to 0.75 for concrete. You could remember this value while doing calculation. If not provided, you should use it. The cohesion of the material for permissible shear stress at the plane considered. So that is 1.4 Newton mm square for concrete. Both are the standard values from your concrete, and they can be taken. So this is what cohesion of the material or permissible shear stress. If you multiply by area, this area is difficult, that on which area it is acting. So computation of this area may take a lot of time. Otherwise, this mu and tau c are not difficult to place the value, they are almost constant. Now, this mu is multiplied, the internal friction, to the net vertical forces. This is downward, the weight of the dam W, and Pu is the uplift acting upward. So net vertical forces acting downward is taken and multiplied by the mu divided by F5. What is F5? Partial factor of safety in respect of friction. So partial factor of safety, will see that how much should be. There is provision in the IS code what the value should be of Fi and Fc. And what is Fc? Partial factor of safety in respect to cohesion. So these two are from should be taken from the code. And what we look at, that this factor of safety for sliding is having two part. One is this and second is this. So clearly this is for the friction and this is for the cohesion, and this is divided by the horizontal forces, because these are detrimental forces. These are causing the sliding. They are taken. Some certain forces are also, like tailwater is negative, having negative value. So we will take the summation of all positive, negative, and the net forces are net horizontal forces are considered here for calculation. Now to understand this, we need to calculate all these values and to place. Why I have mentioned that the calculation of this area where this tau c is acting is important, because if we are calculating, we are considering the base, it's okay. Otherwise, at different level, we will get the value of A different at level, say below 5 meter, 10 meter, 20 meter. So it would be a variable quantity. This is F5. This is value of FC. This is load combination critical. This is empty. While construction, this is normal reservoir, and this is the flooding condition. All three, then value of F5 is taken 1.5. That is when we are considering mu, internal friction, and for this 5C for cohesion, for dams and the contact plane with foundation 3.6. For foundation, thoroughly investigated for, and for others 4.5. If investigation means you have not done boring and you have not taken the geological logs into consideration, you haven't gone through the reports of the geological part of that area, then consider this FC as 4.5. And if it is investigation done, like Sadas rover many technical investigation has done, including the geological. So you could safely take the value of FC as 4. Okay, for dams and the contact planes with foundation, this should be 3.6. And this is for the foundation. This is for these two values are for the foundation. And DE, you look at this has been reduced because these load combinations are already heavy. Now we cannot take the factor of safety larger in that case. And last two, F and G, inoperative what? The drain condition. So they are taken as 1.5 have been reduced. So basically when we do calculation with the first row ABC and mostly with the C, if we consider, then all these values should be taken. For final design, the value of cohesion and internal friction shall be determined by actual laboratory and field test for large projects. I add it to this. This is for large projects. Large project means the central government define large project as per the fund they are distributing, say 1,000 crore and more. Likewise, so smaller you could define it through area, but through funds also they need to be defined. So that these values of friction need to be determined, should not be taken directly 1.5, 3.6, but you should calculate it, do the experiment in the laboratory. If you are not doing, your team should do. Now the third type of failure, now we are looking at the compression failure. This is a very interesting type of failure, and it will give you understanding about the dam and forces acting on the dam and how the things to be calculated. Because in the first, what we have seen overturning, so we do the summation and everything, the disturbing forces or the forces which are causing the overturning and the righting moment. In second, we take the planes at different level, but in crushing, the compression failure or crushing failure, what we do, we take the base of the dam. This is base of the dam. This is base of the dam. And we do the analysis here only to check whether this toe is safe or not. This will crush under the conditions which are adverse or favorable. And the resultant force R, this resultant force R, which acts at the CG of all the forces. This is point center of gravity or CG. Okay, and these are the summation of horizontal forces, all forces. Here, all forces we are considering, and we are summing up their horizontal component. Here we are summing up or subtracting the vertical component for sigma FB. Now, this seems to be your writing moment, because resultant is here horizontal, this is disturbing or the overturning moment. Here in crushing, what it states that this resultant force, I remove again to explain you in this resultant force R, if it is within or inside the toe, like here, then it's okay. Your design is okay. But the condition of it is going out of this like this. Then what will happen that this toe will fail because the permissible stresses here would exceed the existing stresses here would exceed the permissible stresses of the concrete, and this concrete will fail in compression or will get crushed. And once it is crushed, means what? The total base width, what we need, b by 2 is the total b. This is from here to here is the base width or breadth of the dam, and this is almost 80% of the height of the dam. This is thumb rule that the base width is almost 80% of the height of the dam. So if your height is 100 story, then you will see that this base width is around 70 to 80 stories. This is thumb rule. I'm talking about gravity dams, not about the arch dams. No, only the gravity dams. So once this base breadth is reduced, means the concentration of these forces and stresses become more and failure is inevitable. Second thing, when we look at these forces, then we could divide the base into two parts, b by 2, b by 2. Ideally, this R should act here. If we could design this structure, this is just part of the structure. If we could design this structure as if R is passing through b by 2, then it is most safe. But I don't think that you could do that because it becomes uneconomical. For that, we need lot of concrete here and there. If we want to shift this a little this way, then we have to dump concreting here. More and more concreting to be dumped over here to keep it at the center. So that is not possible. Means thrice the cost what you do with the present type of calculation. So R is shifted from the middle of this base towards the toe, and whatever is the shift is called the eccentricity. Whatever is the shift is eccentricity, and the remaining part from the toe to the eccentricity, or you can say point at which this resultant in cutting the base is x bar. This distance is taken as x bar. Okay, so eccentricity, why eccentricity? Ideally, R should be passing at b by 2. But since it is shifted towards toe, then an eccentricity has been introduced in the calculation or in the picture, and that eccentricity should be calculated. The value of E is very critical. Mind it, the value of E is very critical. We are fond of calculating value of E. It should not be more than B by 6 at any level. It should not be more than B by 6. We'll see why this is B by 6. So the total is B by 2 here, from here to here, but this eccentricity here, we say that this should be less than B by 6. Why? We'll see the calculation mentioned in the following slides. This should not be, this should be less than B by 6. So let's see here. This is compression or crushing. In order to calculate the normal stress distribution, normal stress distribution means summation of direct and bending stresses. Normal, in order to calculate normal stress distribution at the base or at any section, these sigma FH, sigma FV and R resultant, and XR is calculated as sigma MR, sigma MO. This is writing, and this is overturning moment divided by sigma FV. This is force. This will give you the value of X bar. You are very familiar that how the eccentricity and X bar to be calculated. So I think this formula is okay with you, that the two moments which are there, one is disturbing, which is MO, and which one is the stabilizing, which is MR, writing and overturning, and we take the difference and then we divide it with the sigma FV, that will give us X bar, value of X bar, and E is B by 2 minus X bar. This is the definition of E, that if we reduce X bar we have calculated from half of the base width of the dam. So we'll get value of E. Now use this value in these two types of stresses. One is the direct stress. We do the calculation for direct stress, and second is the bending stresses. So direct stresses means this vertical component divided by the base. We take the unit length or length 1. This is B into L. So sigma CC, vertical component of the force, direct stresses here at the base are this, and the length is taken as unit. So that is considered 1. And the bending stresses is sigma C BC plus minus My by I. And this is Y is the maximum value could be B by 2. This is from the center here, increasing this direction. And I is the, what is I? Inertia. And sigma M here represents this FV into E. This is introducing the eccentricity, basically introducing the moment, and we multiply by the Y and we put the value of I here. I is IB cube, moment of inertia, divided by 12 for a rectangular section having 1 meter width and B depth. Then this can be the equation used. And if you put up the values of sigma CC and sigma CBC, then we get the normal stresses. So total normal, the total normal stress Pn, the value of this, if we put up sigma FVB this, then this is the equation, that sigma FV divided by the base in bracket 1 plus minus 6E by B. So this B by 6 will come from this equation. I said that it should be less than B by 6. So this B by 6 is important. We'll see in the next slide why this B by 6 and how it changes the stress calculation. The positive sign will be used for calculation of normal stress at the toe, since the bending stresses will be compressive there. Are you getting this? This positive signature, positive sign would be taken only at toe and negative would be taken at heel to calculate the stresses, normal stresses. So let's see here. This is equation. This is heel. This is toe. And we are going to use this equation which equation? Sigma FV by B 1 plus minus 6E by B here to calculate the stresses. These are stress diagram, normal stress diagram 1, condition 2, condition. What are the condition? When the value of E is less than B by 6, when condition second is when E is exactly B by 6, when E is greater than B by 6, 3 conditions. Now, when E is less than B by 6, then what will happen here? If E is less than B by 6, then this doesn't become negative at heel, because when we put minus sign here for the heel, this calculation, this remains positive. This won't be negative, won't become negative. So here at P heel we'll get some compressive stresses, not the tensile stresses, and the total compression. So whole stress diagram, normal stress diagram, yeah, normal PN diagram is in compression. But when E becomes B by 6, then here, if you look at it, becomes 0. PN become 0 at heel. So this is the calculation, and at the toe it becomes twice the sigma FV by B. So this is the condition. And when E is greater than B by 6, then it crosses the baseline, this reference line, and it goes up into the tensile zone. This is tensile zone, this is compression zone or compression area. So this becomes tensile and negative stresses would generate. And what will happen? The point till there are tensile stresses, these negative stresses, a crack of length LC would generate. This is the length of crack, and here we are getting the compression. So this equation of compression failure or crushing failure to calculate the total normal stress PN gives us insight into understanding the behavior or distribution of stresses at the base and how and why the resultant should be kept within the limit. So we are checking that, and we'll look at the calculations further onto it. Now, the third calculation to do the fourth type of failure is the tension failure. We have seen the third case when your E, the eccentricity is more than B by 6. It becomes more than B by 6. Here, this eccentricity becomes more than B by 6. Then what will happen? That the tension will develop where at the heel, the length of the tension crack generated at the heel, LC, can be calculated by taking this condition. By considering this condition, that to develop the tension crack, we are making the direct stresses and bending stresses equal, and we are putting up the value. And what we are doing, we are converting this. Why? How? When the eccentricity E is greater than B by 6, a crack of LC will develop due to the tension, which can be calculated like this, and the value of Y is taken as B by 2 minus LC. And if we do the calculation, then the LC comes out as B by 2, 1 minus B6 by E. This is just an equation. Many a times, like in the uplift pressure calculation, I have given you the length of the tension crack LC directly. But that length of tension crack can be calculated using this equation, and as per this LC, the length of the tension crack, this uplift pressure diagram would change. Are you getting? So that uplift pressure diagram would lead to a kind of failure because of this tension crack which has been generated. If resultant is cutting at base beyond B by 6. So what it states, the resultant should always lie within the middle third. B by 6 is the from center of the base. So B by 6 this side, B by 6 this side. So the total portion of the base, how much it is coming out? This is B by 6 from the center. This is if center and B by 6. Then you could divide into 3 parts. This is B by 3, B by 3 and B by 3. So your resultant should always be here within this length in the middle third. If your resultant is beyond this, then if it is onto this side, then definitely there would be kind of tensile crack getting generated over here, or if it is going beyond it, then there may be overturning kind of thing. So that you need to take care that if going beyond the toy, then overturning kind of thing. If it is going beyond the B by 6 from the center or from the middle third, then there would be tensile cracks getting generated into the system. So this is a golden rule of design of gravity dam. This is called a golden rule, that the resultant of all forces, horizontal and vertical forces, should lie within the middle third of the base. Middle third of the base. So if we could maintain that condition, then our design can be considered as safe. What it states that no tension should be permitted at any point of the dam under any circumstance for moderately high dams. This is important. This is a codal provision that for moderately high dams, which are not too much high, almost say 100 meter, 150 meters like that. For no tension to develop, this is the condition. Now next is in case of extra high dams, 230 to 260 meter, small tension within, just mark this value, the small tension within the permissible limit is generally permitted for comparatively small period of loading. जैसे अर्थक्वेक या वेव फोर्सेस हैं उसके लिए तो हल्का सा टेंशन अलाउड है. ये क्वेश्चन हर जीपीएससी में पूछा जाता है कि कैन वी अलाउ द टेंसाइल स्ट्रेसेस इन हाई ग्रेविटी डैम. Then your answer should not be no. That small amount of tensile stresses are permitted as per the IS 6512. And what are the values? Values are like this. FC is what? Permissible tensile stress. How much? This is just if you multiply by 100, 1%, 2%, 3% or 4%. 2% and 4% for load combination CEFG. These are the conditions for masonry. This is for concrete. This is masonry gravity dams. The half of it exactly. So these are IS code provision where FC is the cube compressive strength, which you study in the 456 IS 456. So that FC is to be taken and multiply by 1%, 2%. This much of stresses, tensile stresses for high dams, extra high dams are permitted, say beyond 200 meters. No tensile stress shall be permitted at the upstream phase for load combination B, normal pool level. This is normal pool level. Small values of tension on downstream phase may be, downstream means below, downstream phase for load may be permitted since it is very improbable that a fully constructed dam is kept empty. And downstream cracks which are not extensive. Downstream cracks which are not extensive because hardly any stress is there. We consider linear variation on horizontal plane. So this is the list stresses on the downstream face of the dam. Not extensive and for limited depths from the surface may not be detrimental to the safety of the structure. You need to study this, digest this statement, so that you could speak confidently. This statement is from the code. And why the tensile stresses are permitted like that. Okay, so now we come to the last slide for today. And the failure which I have mentioned earlier, that because of the tension crack, length of LC, the uplift diagram would change. That earlier when there was no tension crack, this is tension crack mentioned. When there is no tension crack, this is the diagram. I draw it for you. This is the tension diagram. But when there was a tension crack earlier of this length, then what will happen, that we have to take this horizontal up till here and then take a straight line down onto the toe point like this. But since this has been changed, the stress condition P and value of Pn would change, and during the course of time, this length LC would increase, and suppose it is increasing up till here, this is little bit more, then we have to take, as per the code provision, the horizontal length up till here and then take it to the toe. So this is more and more aggressive uplift pressure and reduced weight of self weight of the dam. So what it causing? It will cause this resultant to move. For first condition, this is resultant R1. For second condition, this is resultant R2. And finally, you look at this. This is resultant going cutting the toe and coming out of the toe. If I remove all the, then you could see this is the toe and your resultant for the final condition. This is this. Now this has reduced the effective breadth B of the dam. The tension crack are detrimental. Look at that, though dam is having base width this much from here to here, but effectively which is resisting the forces or stresses Pn is this much only, and our resultant is going out of the toe, and that will lead to overturning, and definitely the tensile crack has already been generated, and this may be detrimental, means failure of the dam. So these are the four different analysis of failure. One is overturning, second is sliding, third is crushing or compression, and fourth is tensile. So you remember failure. Now we understand we have understood the Pn, the normal. We'll next time understand the kind of stresses, different stresses because of the different loading conditions in that dam, and then finally we'll arrive at the elementary height and the higher dams, big dams, the design of big dams. So that will do the calculation in next lecture. So I take your attendance now. I take you back to the portal and show discard. Then I stop recording first. Stop.